going to talk about making learning work, and my first quiz for you is to figure out what are the 3 different meanings of that. There might be more than 3, but I can think of at least 3. One of them in particular is how we, as instructors and developers and scientists, need to work on figuring out what works best and get that into our online course. And that's probably my major emphasis, but I'll give away 2. Another one is making learning work in the sense of getting students more actively involved in the learning process, and that'll be a general theme here. But before I get into it, consistent with those ideas, let's start with some data collection. So I have a set of true-false questions for you, and I'd like you to raise your hands on whether you think each of these statements. Let's start with true. Students learn from lectures and readings. How many think that's true? How many think that's false? Yeah, well, we could do a Likert scale, but I should have said take your clickers out, right? And yeah.
I'm going to say it's false.
Okay, so I don't know. We got about 85% saying yes and maybe 15 no. Assessments motivate learning from lectures and reading. Yes?
Yes.
No? That was more like 50-50. Assessments are learning activities. No? Who says no? Well, those are just elaborations. You can take your pick, huh? I'm not saying they're all true-false statements, right? Students learn quite little from lecture and reading. You want to answer that separately? Yeah. Who says that's true? Who says that's false? Not as many as the first one. How about this? As I listen to a lecture, I know when I'm learning and when I'm not. Who thinks that's true?
Talking about this lecture?
Yeah. No, I really mean the lecture part. Like, if we're doing something interactive, I want to separate that, okay? Yeah. You're not learning anything yet, right? Yeah. How about not? No. So that was maybe 40-60. Okay, learning is a relatively discrete event. Like, you don't know something and then you hear something and now you do. Yes? True? Who says false? Okay, most of you. How about learning happens slowly and continuously? Yes? No's? Couple no's, okay. That was probably the most, well, here's what I think are the right-ish answers. They're not right or wrong, but we'll come back to that later. So one of my favorite quotes in this area comes from one of my favorite academic heroes, Herbert Simon. I guess I should say, as a way of a little bit of background about myself, like Herbert Simon, I've played in between computer science and psychology, having started a PhD program in computer science and then came to Carnegie Mellon to get a PhD in cognitive psychology. But Herb said this many years ago: improvement in post-secondary education will require converting teaching from a solo sport to a community-based research activity. So I want to probe that idea here a bit with you today. And I want to start first by thinking about how we design our online courses today and what steps we might take towards designing them in the future. So I will submit that the primary way in which we do course design is we self-reflect and we bring our intuitions to bear on our content expertise. And we use that in some kind of instructional design process to create our online courses that get used in practice. And these days we're starting to use those online courses to collect data. But I think what's mostly happening with this data right now is that machine learning folks are building predictive models and they're writing papers, right? So I think we can do better than that. And so one element of that is many of you know, is there are lots of theories of learning out there that we can draw upon to help guide our design, right? So that we can apply that learning science in addition to our intuitions and our self-reflections. What do folks think about this? Is this the right way to go? Is this a better way to go? Yeah? Good. Active participant in front. Is this a research activity when you do this? Who says yes to that? Not necessarily. I'm not sure it's a research activity. It's an application activity, right? I don't think this is what Herb Simon meant. I mean, I think he would support it, but I think it doesn't stop there. So what's wrong with this picture? What do I need to add? Data collection feedback, bingo, right? We got to get that line back in here, coming from the left, right? And we got to use that data and the theory to design models of learners. And they need to be explanatory models. They can't just be big predictive machine learning models that we can't understand what's inside. We need explanatory models of learners. And then we can use that, for example, to build a model of the expertise we want students to acquire and drive our instructional design through those models of learners. So not just, we should apply learning science, but not just learning science. We also need an engineering design process to bring learning science and data together to bear. And so that's a major theme for me today. So that gets at the research activity, but what about the community-based? Is this community-based yet? The key to the community-based part is to get the discoveries contributed back from the insights you acquire, the models you build, the data you collect, bring them back to the community. And this has been something I've been very committed to in the work that we've been doing. So we need to build a better engineering design process together. And now that's been a key goal of the recently formed Simon Initiative at CMU, and it's really a collection of a number of things that I will talk about that have been happening at Carnegie Mellon, and our new president, Subir Suresh, when he came, kicked this off. And it's motivated by Herb Simon in many different ways, but I want to tell you a story about sort of how we got to this point and what some of those resources are. So the first part of that is to say a little bit about early work we did with intelligent tutoring systems that apply cognitive psychology. And the early work we did there was focused somewhat on the college level, for example, intelligent tutoring for programming, but also on at the high school level to teach mathematics. So it seems like today we often hear about the coming adaptive technology, but really adaptive technology is not new. It's been around for a long time. These cognitive tutors were providing adaptive instruction since the mid-'80s. The scale issue was definitely not there, so that's a new thing, is the opportunity for scale. But I also will very quickly say that there's plenty of room for improvement in these adaptive technologies. And one of the things we should be thinking more deeply about are the ways in which these technologies can be adaptive. So we think about that in three levels of loops that are temporally more broad. So the step level is adaptive while students working in an activity. Does the system adjust to what they're doing, the errors they're making, the strategies they're taking? That's a fine-grained level of adaptivity, and I'll illustrate that in a second. The next level of adaptiveness is selecting the next tasks for students to do so that it well addresses their needs. And the outermost level of one is illustrated by that data loop, which is when we make an instance of a course, we should collect data on it, or even an existing course, use existing courses to collect data, and then iterate on the design of the course to improve it. And that kind of adaptation is often the most powerful because the insights that come from that broad level of what do all students need get applied the most broadly and they're the easiest to develop. So here's an example of a screen from our high school algebra cognitive tutor, which is part of a full course. We use the cognitive science research to also design the text materials that I'm not going to illustrate. But this is somewhere in the middle of the course. students are working on authentic problems like figuring out which of these cell phone plans that have been described they should pick and under what circumstances. And they're doing that work in essentially a mini spreadsheet. And as they're working through the problem, the tutoring system is tracking what they're doing and is giving them immediate feedback if they make errors. It's asking challenging questions like when do the plans cross over here? And if students are stuck, they can ask for hints and they can get instruction that's personalized to their needs. It's instruction that they've demonstrated a need for by having a difficulty in the context of a complex problem. So that's the step-level adaptation I was referring to. Then, as they're working, a model's being built of what they know and don't know, and that's used to individualize the selection of the next task. And key to all this is having what we sometimes call a cognitive model, a model of what students need to know, or another way to say it is a system that can represent how problems are solved in the domain in the various ways that students can solve problems. So taking a simple example from algebra, here's a state that a student might be in and a couple of different ways they can move forward, represented in general terms, so this would apply across many contexts, as well as a common error a student might make. And if you have a model like this, you can do that step-level adaptation by tracing an individual student's strategy through this space that these rules generate. And then when they need help, you know what state they're in, and you can use one of these rules essentially to generate help for them. So model tracing is the algorithm we use for that step-level adaptation. And then at the higher level, these skill bars, as they're so called, is a model that's assessing students' knowledge growth. One way to do that is through Bayesian estimation methods that we've used, and that then does adaptation through selecting activities and determining the pace. So when all these bars get to the 95% acquisition level, the student's done with that section, for example, and then moves on. So in addition to this adaptive support of learning by doing, another really important part of this is that the data we're logging already has a sort of theory-coded attempt there. We have a theory of what the students are learning. And it turns out, as obvious as it sometimes seems like we know what students need to know, it turns out over and over again when we dig in, we find out what we think they need to know is not what they need to know. So this, usually what happens is we get this theory-coded attempt at what are those skills in these bars, we get it wrong. And the data then shows us how to get it right. So let me give you an example of one of these data-driven adaptations at the design loop. So this was early, and this also illustrates that it doesn't have to be in technology. So at the time we were designing this algebra tutor, I was particularly concerned with how teachers were complaining about the difficulty for students of doing story problems like this one illustrated here. So I created a set of triples like this that are all matched with the same, they all have the same answer, right? And they have different content. This one has a story to it, this one's in words, and this one's just an equation only. And the question was, which of these are going to be hardest, and try to understand why, and what are the interrelationships between these different types of problems. So who thinks, beginning algebra students, the data I'll show you was collected like in March or April of a first-year algebra course. So they've been doing algebra for a while. Which of these is going to show the lowest percent correct, or be the hardest? Story problems? Word problems? Equations? The hardest. You're going to say equation is hardest. That was definitely in the minority response. Why equation?
They'll get confused with the order of operations or something like that.
Yeah. So when we asked math educators and teachers, they said, like most of you, story and word problems are going to be the hardest. And the sort of rational analysis that I did at this point is, well, you solve a story problem by translating it to an equation. So it's got to be harder to do the story or word problem. Maybe the word problem is intermediate in the translation, like the operators are made explicit in it, so it might be easier. But Lorena, you were right. In fact,
Favorite 3 words.
yes. My wife's too, interestingly. Equations were hardest, and we've replicated this a number of times. It was quite striking and surprising. Essentially, the reason is that equations are kind of like a foreign language for an algebra student. And there's a lexicon and a syntax, like order of operations, that actually brains are pretty good at acquiring languages, right, without any verbal instruction. Like nobody tells you how to learn English, right? They can't give you a lecture on learning English because you don't have English yet to learn English. Our brains are really good at picking up the patterns in languages, and we do it very implicitly. And what that produces for us is what we've sometimes called an expert blind spot. I kind of regret this because it turns out that data suggests that that we're not just blind to some of what we know, we're blind to most of what we know. About 70% of what an expert knows, they don't know they know. There's all kinds of great examples of that if you want to ask me about, I can tell you about. But this is one of them. The algebra teachers especially were incorrectly thought that the equations would be easiest. So what do you do with this kind of data? It really reframes how you approach the course and how you approach the sequencing of the material, right? Now we can actually use story problems as a kind of introduction to the formal notation and help teach them the foreign language of the notation as a translation to something they already understand, right? They understand the English. It really had a big influence on the design of the system, and we did some tighter experiments to demonstrate that we could use this idea to improve student learning. But more broadly, we also built this whole course, and a number of data-driven insights like this led to a curriculum that has been in pretty widespread use. In 1998, we spun off a company to get it out into schools. About 500,000 or more students use it every year as part of a full course. And there have been a number of field trials. One of the early studies I did is illustrated here. Probably the biggest randomized field trial of educational technology ever run is this one. It's published in 2013. Involved about 140 schools that were in a random assignment experiment to either get this technology-based course or not. There's a lot of subtleties to that study, but in the second year of implementation, a major result was that the students in the cognitive tutor course, as illustrated here, essentially learned twice as much over the school year as students in the control condition. Turns out one of the rather shocking things about this, and this goes to slowly and continuously learning, is that the gains in all cases weren't as big as you might think or you might hope across these 140 schools. So doubling a relatively small amount of gain is still a little sad. So that brings me to an important point, which is our work is still cut out for us. We could do better, but it's also the case that we made so many decisions that were uninformed by science and uninformed by data. I gave you an example of one that was informed by data, but most of our decisions were not. We were doing what we mostly do in instructional design. We were winging it, right? I think we can do better, and what we need, and I think the opportunity that's emerging with OPENEDX is to have an infrastructure that supports that, right? And fortunately for us, in 2004, NSF was starting this Science of Learning Center program, and we were funded as one of 6 Science of Learning centers, and got a substantial amount of funding over a 10-year period for that. We had built on fielded educational technologies like this Algebra Cognitive Tutor, like the Open Learning Initiative courses that I'll tell you about in a moment, as well as some other technologies for language learning and some educational games. And a key idea that we had early on in this 10-year project was that we could use the educational technology to get learning researchers out of their labs and start studying student learning in the real world, in the context of these courses, right? So that's a kind of basic research at scale idea. And what we were trying to facilitate is if you try an instructional design out in a tightly controlled experiment, don't just do it in your lab, bring it out into one of these courses and let's see how it works with real students. So part of the center's goal was to create a kind of social process, not just a technical process, for allowing researchers to do studies in schools more easily. And what we facilitated is We call these in vivo experiments. You might, similar to the idea in industry of A/B test, we're comparing two very closely related versions of a course design to each other. We also collected lots of data, and that data is now available in our DataShop data repository, which is shown here. And you can go here and poke around, say what kind of person you are and what kinds of goals you have, and we'll show you data sets and papers that have been written about those data sets, and you can start digging in. You can also upload your own data, and this is tricky, but is made as easy as possible so that you can, for example, use a tab-delimited file format to upload data. And a lot of the data that's now there has been so uploaded. And then key part of the analytics there is to allow you to look at how students are learning over time, and I'll illustrate that in a moment. What did we learn more deeply about how to design this engineering design process? That's what I want to tell you about a little bit more now. Some of the lessons that we learned over this process were published in this 2012 paper in the Cognitive Science Journal on our knowledge learning instruction framework, or we call it the CLE framework. And broadly speaking, part of what we were trying to do is create a set of taxonomies to think more carefully about the difference between instruction and learning, and the difference between learning and acquiring skill, and the difference between acquiring skill and demonstrating it on assessments. And the circles there represent things we can see, and the squares or rectangles represent things we can only infer. And a very important notion there is that you cannot see learning. And I think we feel, like a lot of you said, when you're listening to a lecture, you can tell if you're learning or not. I'll show you some data in a second that I hope makes you question that idea. It often feels like we know whether we're learning or not. But the learning isn't about what's happening now. The learning is about changes that are happening in your brain that'll get reflected later in your future performance, right? And you can't really tell if those changes are happening in a way that'll be lasting and that'll transfer to new situations. So part of the goal here is then to create a finer sense of what's going on here and how you can use what you can observe to make reliable inferences about learning and knowledge construction. And one of the things we recognized as we had lots of experiments happening in these various courses is how complex instructional design is. And you wouldn't know that if you read the newspaper, right? Because there's usually these wars in math about, should you teach the basics or should you teach, understanding or reading wars, as if there's always two things, right? Researchers seem to like two things too. They have things like, should you focus practice or mass it, or should it be distributed? But in fact, there's often intermediate ground, like you should gradually widen, right? But worse than that, that's not the only decision, right? There's another decision related to how many examples should you give as compared to problem solving or activities for students, and should there be some intermediate mix? And if we put these two dimensions together, now we're up to 9 different ways to teach. And maybe you see where this is going. But there are lots of other choices to be made. Should my examples be more concrete, because those are easier for students, or should they be more abstract, because that fosters transfer? Should the feedback in an interactive system be immediate while it's in the student's head, or delayed so they think harder about it? Should I block topics into chapters so we're working on the same thing for a long time and you really get it? Or should they be interleaved so that you understand when to choose one approach versus the other? None of these, by the way, there's a lot of literature on every one of these dimensions, but the results are almost always mixed, and it depends. And the dependencies aren't random, but they're complicated. The bottom line of this analysis is that there's just tons of different ways to teach. Like our combinatorics suggested 205 trillion different ways to teach. So that's the challenge in front of us at some level. And big data is a huge opportunity to meet this challenge, right? We can collect data from our courses and try to approach this huge challenge of what's the best way to do instruction. Across many different domains, we had a lot of language learning domains in the center, math learning, science learning. We created this taxonomy in the CLE framework that distinguishes, there's a finer level distinction here, but I won't go into the details, but roughly speaking, you can think of things that are facts. They're kind of mappings between some constant like what's teacher in English and some other constant like the Chinese word for teacher. Or rules or skills, which are kind of variable mappings, like the area of a particular triangle with this base and height is this particular value. Or principles that have rationales and that can be understood. You can take those different kinds of knowledge and arrange them in some sense of complexity, simpler on the left and here and more complex on the right. And then you can also list out different instructional approaches. And there are many books out there that'll give you research on that complex, on dimensions in that complex space I just told you about. And here are some examples. And over here is a taxonomy, a rough high-level taxonomy of the different kinds of learning processes that are afforded. So memory and fluency, induction and refinement, understanding and sense-making. And the key observation that we came to is that the nature of what works best is dependent on the kind of knowledge that you're after. And these plus signs are positive results of controlled experiments applying this principle like optimized scheduling to Chinese vocabulary or to geometry rules. And there are some zeros here, and there's a sense of a kind of boundary up here which suggests that certain complex forms of instruction just aren't very effective and certainly not very efficient for learning simpler kinds of things. There is a kind of correspondence here, and then some question about what's happening in this lower triangle. But basically, the key notion here is that optimal instruction depends on the nature of the knowledge that you're trying to teach. So here's a place where data and modeling of the domain is essential, and it's one of three reasons. So it's essential because it helps you pick which instructional principles to apply, and so that I just discussed. It also helps tell you how to apply them. Like one of these principles is multimedia. Like if you're teaching a process, you should have a diagram of that process along with verbal description of that. And there's another principle, modality, that suggests that description should be better in speech than in visual text. But choosing what the diagram should be and what it should be about requires getting the knowledge of the domain right. And that's all I'll say about that for now. But a really key notion is how modeling domain cognition can be really fundamental to producing high course quality. So let me try to illustrate that. And this comes under the heading of cognitive task analysis. I'm curious, how many have heard that phrase before, cognitive task analysis? How many have done a cognitive task analysis? 1.5? Yeah. The goal there is to identify the underlying cognitive processes that students need to learn, essentially to create an accurate cognitive model. And as I hope my algebra example started to give you a sense of how our intuitions aren't always accurate about what are the cognitive processes that are troublesome for students. There are many methods to do this. Herb Simon did a lot of think-alouds with people to see how they solved problems, and that led to research on building chess-playing computer programs because they got a deep understanding of how the thinking process works in chess. You can build computational cognitive models of this. By the way, when I say cognitive model, I don't mean necessarily an implemented one. It can be just an explicated sense of what are the skills, facts, and principles needed to do well in a domain. There's structured interview approaches, and there's some quantitative approaches that we've approached. One of the reasons I wanted to see this sampling is because I do think it's surprising at some level that how little known this technique is, because for my money, it's probably the most powerful. If you're going to do one thing, forget about all those instructional principles. Think about what tasks you want students to do towards what end. What do you want them to be able to think? And do cognitive task analysis to figure out what you want them to be able to think and do. Among these methods, one we've been working hard on is to leverage all this data exhaust from these courses, right? And that's that learning curve idea. And the key notion is that if your cognitive model is good, then when you use it to look at your data, you should get good learning curves. They should look smooth. So this is an empirical engine for discovering a quality cognitive model. If it's not smoothly declining, if there are blips in it, or if it's flat, then there's something wrong with your cognitive model. So let me give you an example. So here's an error rate learning curve, right, where on the x-axis there are opportunities for students to practice. And I'm going to show you data from a high school geometry course, a unit on area, like finding the area of a circle, an area of a rectangle, that sort of thing. And then we're going to average across every student and every skill what their correctness is as we go off to the right here. And so what should happen in a good learning curve? The error rate should go down, right? So here's an actual learning curve. If you assume that there's one knowledge component for geometry area, let's call it geometry area, it doesn't go down in error rate. As you practice geometry area problems more, you don't necessarily get better at geometry area in general. Why are the errors going up? Just think, I mean, this is a typical course sequence, right? We're starting with simpler things like rectangle area, right? Moving to harder things like triangle and trapezoid and circle area. So those blips in error rate are when the content changes, right? So there's the empirical indicator. I mean, this is an obviously wrong model of the skill, but it's not really too far away from what we sometimes think, right? The topic is geometry area, right? Are you getting better at it or not? It's not the right level of analysis. This graph's taken out of DataShop. You can display a knowledge component model with one knowledge component in DataShop. And when you do that, there's no smooth learning curve. But if you take this exact same data and recode it with, say, 12 knowledge components or skills, same data is now a smooth declining error rate learning curve. The blue line there is a statistical model. It's a generalization of item response theory. But the real upshot here is that you can do this more generally. You can automate this analysis and produce better cognitive models. Turns out in this data set, there's a model with about 19 knowledge components that fits the data better than this one. So the work wasn't done. I'll give you an example of that. But here's what you can do then, is you have a version of your online course, you deploy it, you collect data like this, you look at the learning curves, you make some discoveries, and then you make some design changes, and then you incorporate that design into the new version of course and do your A/B test and see if it turns out better. So we did that in this case. Those 12 knowledge components, one of them was called compose by addition. It's a kind of weird one, but that's one where students, there's not one formula that works because it's some irregular shape, like what happens when you cut a circle out of a rectangle, what's the leftover area? You have to compose two formulas to come up with them and either add them or subtract them. This accounted for both. But a lot of these curves do go down like circle area, but this one was flat. So high rough curve means you've got to revise the skill model. We did that. We basically identified that we were scaffolding the planning process in some problems, and they had lower error rate. But then when we removed the scaffolding, the error rate went up. We weren't really focusing the instruction well enough on the planning. So we redesigned that instruction. And one thing we did that was, I think, particularly interesting is that we developed, I showed you this complex cognitive tutor, but what really worked in this particular case is we made simple multiple choice questions that asked students, what's your plan? How are you going to find that irregular area, right? And they just selected from options. I'm going to multiply the height times the radius, right? Or I'm going to I'm going to find the area of the circle and subtract it from the area of the square, right? So you could isolate that planning skill very efficiently. And we did that. We created a version. We did an A/B test. And what we found is students reach mastery according to those skills much faster, but they got much more practice on those hard-to-learn planning skills, and we wasted less of their time on the simple area problems they knew, reduced time to mastery by 25%, and they actually did better on the post-assessment, especially on these planning questions. sometimes people say, I don't know if it's that important that you can reduce time by 25%. But I don't know, if you think about a parent paying for their student's college, and you could say you could pay for 3 years or 4 years, right? That's a 25% reduction there from 4 to 3. I think that would be good. Yeah, and it's not like they have to go away. We could start teaching them more complicated things in the 4th year, right? So my last topic here is learning by doing effects and MOOCs. And I want to say a little bit more about how we moved into the college level space. And that was through the Open Learning Initiative. Around about 2001, we had a visit from the Hewlett Foundation. And they started the MIT open courseware effort, and they wanted to do more open stuff. And but we really wanted to focus on highly interactive courses, and push forward the interactivity. Candace Till was with us at that time, and she was leading the project. Now Norm Beer leads it. Candace has moved to Stanford with John and is continuing the effort. And we are both, Norm and me and Candace, we're all working towards figuring out how we can better integrate with the OpenEDX software infrastructure. And there are details I could go into about that. But OLI now has about 30 full, highly interactive courses. They're available. You can go to the website and use any of them at any time. But there's also installations at various places that are 4-credit installations. Just some statistics here since 2006, the number of academic enrollments. So these are actually 4-credit enrollments. So up to some 450,000 students per year here are using these various courses. There's a big emphasis on identifying specific learning challenges, is sort of essentially this cognitive modeling idea, and then giving students practice at synthesizing and applying skills and knowledge. This is an example from the chemistry course where there's this laboratory simulation environment, and there's some great problems, for instance, about figuring out what's wrong with the water in Bangladesh and how you can use stoichiometry to figure out what's going on there. So applied problem solving. Another one of the courses that's been researched a lot is the first-year statistics course. And there's a demonstration that Candace Till and Marcia Lovett, who's the head of our learning center at CMU now and a cognitive psychologist by trade. In this particular study, actually there's 3 studies, but the culminating one compared a traditional course, semester-long course, takes students about 100 hours. They used this chaos test, which is kind of like statistics answers to the physics force concept inventory. It's the assessment of, I can't remember now, comprehensive assessment of statistics maybe is the chaos test. That test showed a 3% learning gain from that traditional course. The kind of strategies that I was talking about, cognitive task analysis, were brought to bear. It was really interesting working with faculty and saying, what, students don't think about the data type before they select a data representation? They don't think, oh, it's discrete versus continuous. In fact, the experts don't even mention that in their think-alouds, but it's clear from analyzing them that that's a key step in their process, but they never articulate it to students. And so the course clearly makes that a sub-goal in problem solving, just to give you one of these kinds of insights, right? So the data-driven course is now, in this experiment, used in a blended version for half a semester. And then we look at the same learning outcomes. So students spend actually less than 50 hours because they're meeting 2 days a week instead of 3 days a week. The instructor, who's skeptical at first, ends up loving it because they're seeing the data about students' progress. And there's a variation on the flipped classroom here. This isn't watch the video before coming and meeting and doing problem solving. It's almost the other flip. It's do your homework before we meet. Then I'll look at how you're struggling, and we'll talk about where your struggles are, and then go off and practice some more, right? But the flipping, in some ways, is flipping the work to be more upfront. 18% learning gain with half the time from this. Really powerful result. So one thing that I've been wondering is, can we see this power of interactive learning by doing? Is it apparent in MOOC data? Are there MOOCs with lots of interactive learning by doing opportunities? Definitely yes, right? Do students vary in how much they do? Well, that we didn't know for sure. Do they vary in how much they watch the videos? Do they vary in how much they read the online materials? I don't know, what are your intuitions? I mean, yeah, they have to vary, right? But I guess, do they uniformly vary, or could you imagine that some students do a lot of the activities but skip the videos, right? Indeed, I'll show you data, that's what we found. But what are the consequences? Does watching video enhance learning? Does doing activities enhance learning? By how much? And given what we find out, what should we emphasize to students and what should we emphasize in our course development? So we had this cool opportunity where one of the Coursera MOOCs that was developed out of Georgia Tech, they decided to embed as available material for students the OLI psychology course, which is a full online text with tons of interactive activities in it. So that on the Coursera side, they did their video lectures and their slides, and there was a discussion forum, and they had writing assignments, and they had quizzes. They were actually drawn from the OLI item banks, and they had a final exam created by the instructor. OLI has expository content that you can essentially read or watch video clips. It's mostly text and examples and images, but then a lot of interactive activities with the kind of cognitive tutor feedback and hints that we were talking about earlier, sort of being brought to the college level. I'll give you an example of it in a second. But very important part, again, the design is to align these to the learning objective. There's some cognitive model of the expertise you want students to acquire that these things were being designed towards. So, you've got your MOOCs, and we're going to define a variable in the data that estimates how often students are watching. And you have your online readings. So this is a page from the module 34 on personality as traits. There's an explicit learning objective. There's some text. There's a table down here, right? And then embedded in these pages are interactive activities like this one. Actually, I'll skip to the next slide because I think the video will work. So here, students are being asked to complete the table by dragging each of the major factors of personality based on the 5-factor Big Five model of personality in their proper location here. So it's not a lot more sophisticated than multiple choice, but a little bit. But again, the point isn't the form, the point is the content, right? This is designed to address the goals that have been articulated of being important. But also what's really important, and I hope you saw it illustrated, is students are getting immediate feedback, and they can ask for hints at any point. So the instruction's embedded. The question that we're going to look at in the data is which of these things, watching, reading, and doing, how much do students do, how do they vary, and what impact does it have on the quiz scores and the exam scores? But I want to do a little detour before I say that because I want to sort of emphasize some of the research out there on whether people, like MOOC students, but all of us really, are able to make good decisions about what leads to the most learning. So the simple answer is no, especially students are not very good at doing this. We experience illusions of knowing and learning. We definitely have strong feelings listening to a lecture that you're learning or you're not learning. Maybe you think you're not learning from this, but that might be a good sign. And here's some of the evidence for that. Students are poor judges at what they've learned. So you can ask, for example, in one study, medical students to estimate after having watched a lecture and done some readings, how much they know. And then you have them take a test and you compare their predictions to the actual test, right? Or another study, experienced physicians rate their communication skills as compared to other people rating them. Very low correlation. A different but related idea, students do not learn best from what they like best. There's really low correlation between students' course ratings and after training skills, right? They're different things. They're probably both important, obviously, but they're not the same thing. We can't infer because they liked it, they learned a lot. This is kind of detailed data, but this is one more tightly controlled studies where they had subjects reading a lot of baseball texts and then rating how much they learned from the text and then giving them questions to see. And the y-axis is the correlation between their rating and what they actually did. And you can see there are as many points that are negative as positive, right? There's almost no reliable correlation in the people's ability to calibrate what they're learning. And why is this? Basically, students have insufficient mental resources to both learn and reflect on their learning. The learning's hard enough, right? And besides, they really don't know the difference between right and wrong. That's part of what they're learning. So how could they tell, right? I think in some ways it makes sense. So let's keep that in mind when we look at this data. So here's the data from the psychology MOOC in a kind of exploratory data analysis where I simply did a median split. I cut the students in half in 3 different ways, whether they were on the low or high half of doing, whether they're on the low or high half of reading, whether they're on the low or high half of watching, and then there are 8 categories, right? And this is the number of students out of 1,000 who took the final exam. So this is low in everything, and as you'll see, that in the MOOC is the most popular category. High in everything is the next most popular category. So there's definitely a correlation. If you do a lot, you do a lot of everything. If you do a little, you do a little of everything. But what I want you to notice is that there's at least 60 students in every one of the other categories, right? So this is a person who's just doing a lot, but not watching a lot and not reading a lot. This is one who's just watching a lot, but not doing or reading a lot, and so forth. So now I'll show you the same bars, but now what's their quiz performance in these 8 groups? So just to start with the first one, if you're low watcher and low reader, but you do a lot, there's a big impact on your overall quiz performance. Here are the rest of the bars. This is watching only versus doing only, so bigger impact of doing than watching. Reading only versus doing only. And notice, at least for the quizzes, as long as you're doing a lot, it doesn't seem to matter so much how much reading and watching you're doing. The final exam is a little bit different. You actually see an increase here somewhat, so that doing, again, is the primary factor, but there's some effect of watching and reading. And we built a more complicated regression model, which has, I think, all kinds of assumptions that probably aren't right about linear relationships between these things. In fact, there's some exploratory data in the paper that suggests some nonlinearities that are important. But as a sort of straightforward thing, this is a causal model built in this package called Tetrad. And what I want to highlight is, first, we have a predictor of the quiz performance from pretest, and that has, for every standard deviation you're better on the pretest, you're 0.25 standard deviations better on the quiz score. So these are all standardized coefficients. So let's look at watching the video lecture. That's represented in this link. 0.06 standard deviations better for watching. So it's a positive and significant effect, but it's smallish. And reading's about the same effect. The doing effect, on the other hand, is much bigger, and it's also much bigger than the pretest effect. So it's not just about what you know coming in. If you work hard, right, make learning work, if you work hard, you learn a lot, and you can learn a lot more than you did know. And the benefit of doing here, correlational data, so we should be cautious, even if it's a, quote, causal model, but the association is 6 times bigger for doing than for watching or reading.